In this module, we're going to talk about how to read electron configurations from the periodic table. Really useful. So this is how chemists do it. This is how we read the periodic table. So first, let's look at how the periodic table is organized. If you remember this diagram, I showed you this back in the module when we were talking about the Aufbau principle, which says that electrons go into the lowest energy orbital that has room, and the Pauli exclusion rule that said that no more than 2 electrons can go into any given orbital. And so 1s is the lowest energy subshell, then 2s, then 2p, and so on, as long as there's 2 or more electrons in the atom, which almost always is the case for us. So if you look at the periodic table, you'll notice that after a p subshell is full, what does that mean? Well, because a p subshell has 3 orbitals in it, and each orbital can hold at most 2 electrons, the p subshell, any p subshell, will be full when it has a total of 6 electrons in it. So once we hit 6 electrons in a p subshell, the periodic table wraps around and starts another row. Except for the first row. Well, in the first row, which is where we have the 1s subshell, n equals 1, has no p subshell. There is no such thing as a 1p subshell. So instead of wrapping around after we fill the p subshell, we wrap around after we fill that 1s, just for that time. Now, sometimes it makes sense actually to think about helium as being over here, but most of the time we write it this way. So when we're looking at the periodic table, we know that every time we hit the end of a row, the last column, except for the first one is the electron configuration for that element is 1s2, the element ends in p6, and the number before that, remember the number represents n, or the principal quantum number of the shell, is the same as the row number. This is row 1, row 2, row 3, and so on. That's really, okay, so we're going to use that to read electron configurations. Remember, 6 electrons in the p subshell in the end, except for the first, which is 2 electrons. Another thing while we're here is that the alkali metals and alkaline earth metals, okay, the last column in that sort of those two is always something S2. Let's look at that. So this is a periodic table colored according to these different blocks: the S block, the P block, the D block, and the F block. And so if you look at when we start writing electron configurations from here, you'll see that everything in the first column ends in something S1. And that something is the row number. And S1, we say 1S1, 2S1, 3S1, 4S1, and so on. Everything in the second column ends in S2. 2S2, 3S2, 4S2. The only S2 that's not here is helium. We stick that over there. Okay. And so on. So a really useful thing to know is that the last element in the S block ends in NS2, where N is the row number. Every element in the P block ends in NP6, where N is, again, the row number. So the last element in the 5th row, the P block, ends in 5P6. Every element in the D block, these are the transition metals, the D block, the purple one down here, ends in N-1. Remember that, N-1, D10. So if we're in the 4th row, 4th period, the last element here will be 3D10. Everything here is 1, N-1. And the lanthanides and the actinides we call the F block, 4F and 5F, and those are N-2F. 14 is the last element. Everything in here is N-2F something. So we're in the 6th period. 6 minus 2 is 4. These are 4F. 7th period. 7 minus 2 is 5. 5F. Everything, except for some exceptions I'm going to give you in a minute, okay, in the first column ends in S1, second in S2. In the D block, D1, D2, D3, D4, D5, and so on. P block, P1, P2, P3, etc. And the F block, F1, F2, F3, F4, and so on. So when we use the periodic table to read an electron configuration, all we have to do is say the electron configuration of the last element in each block until we get to the block where our element is, and then just count over. For example, let's say we were going to read the electron configuration for silicon, which is right here. Okay, we would go, okay, the last reading left to right. By the way, we read the periodic table left to right, top to bottom, just like you read a book, left to right, top to bottom. So the last element in the first, as we go through the first row, the last element is helium. It's 1s2. So let's write this down. So we're doing silicon. Let's do it right here. We would say last element in this one is 1s2. Then we come down to the second row. The last element here is 2s2. We're just reading it right through. And then the last element in this row is 2p6. Remember, this is silicon right here. This is what we're aiming for. All right. Then we come past 2p6. Then we get down to here. We're past this s block, so we say 3s2. Now we get to the block that we're in. So we just, okay, it's in the third row, the p block. We say 3p. And then it's in the 1, 2 second column, so we say 3p2, just like that. Let's do one more. Let's say we were going to read the element that's in the, let's say nickel. Let's get rid of some of this so we can read it. So nickel, we would just go left to right, top to bottom, the last element in each block, 1s2, then 2s2, and then 2p6, and then 3s2, 3p6. Here's nickel. So we're past the s block, so we say 4s2. Remember, everything here is S2. And now we're in the block where our element is. It's in the 3D block. Remember, one less than the row number. And it's the 1, 2, 3, 4, 5, 6, 7, 8th over. So we say 3D8. Okay, you got that? Now, there are some exceptions to the order of filling. It ends up the more you go down, the lower you are in the periodic table, the more exceptions end up popping up. I'm going to ask you guys to memorize only a few of them, all right? I'm going to write them right here for you. Let's see if this will show up. So these exceptions are chromium, copper, molybdenum, silver, and gold. And they follow a pattern. The electron configuration for chromium is not 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4, but rather it is, and just memorize this, put it on your card if you have to, it's 4s1, 3d5. Likewise, molybdenum is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1, 4d5. Make sure you understand how we're writing these down. Now we're past the S4S, so 4S2. We're past the 3D, so 3D10, right? And minus 1D10. 4P6. Let's get this out of the way. Then after 4p6, 5s1, not 5s2 like you normally would put. And then 4d5. Why is this? Well, it ends up that it's just a little bit more stable for an atom to have a half full or a full subshell than to not to. This is a general principle that's good to remember. Let's write it down. So remember, okay, going back to here, a D block can hold 10 electrons. Okay, half full, that's 5. And remember, from Hund's rule, we know that's 1 electron in each of those d orbitals, all with the same spin. So here, okay, 5s1, 4d5, the s subshell is half full, because it can hold 2 at most. The d subshell is half full. That little bit of extra stability makes it preferable for the molybdenum atom, for example, to have this electron configuration rather than 5s2, 4d4, which you'd normally expect just following the rules. Now, these guys right here, same idea, except it's going to be s1d10. For example, copper. Let's just do that one. One S2, 2s2, 2p6, 3s2, 3p6, not 4s2 but 4s1, and 3d10. Now copper has a half full at 4s subshell and a full 3d subshell. That's more stable than a full 4s subshell and neither full nor half full with, like, if it was 4s2, 3d9, which you'd normally expect. Silver is the same. It's going to be 5s1, 4d10. Gold will be 6s1, 5d10. So memorize these 5 exceptions. Other than that, what we'll do is we'll just follow the order of filling that we get from looking at the periodic table. Just so you understand, there are more exceptions down here. We're not going to bother with them.